Alrighty, in this video we are going to be doing related rates in terms of substitution and geometry. So let's look at number 7 and number 8 and see what I mean here. So we have the water and it runs into a conical tank at a rate of 2 feet cubed per minute. Before I do anything, I'm going to go ahead and draw my little cone. And I know that my water is increasing at a rate of 2 feet cubed per minute. The tank stands with the point down and has a height of 10 feet. So I have a height of 10 feet and a base diameter of 10 feet. Now, think about the volume of a cone. Remember that the volume of a cone is in terms of R. So what I am going to do is say that R is 5 feet here. Okay, it's asking us how fast is the water level rising when the water is 6 feet deep. So we want to figure out what dH/dt is when my water is 6 feet deep. Now, they gave us 10 and they gave us 5. But we want when the water is 6 feet deep. So we want H is actually being 6. Now, they kind of gave us the information here because we aren't given anything about dH/dt, which is what we're trying to find. But more importantly, we don't know anything about dR/dt. Now, remember back in our intro to related rates video, and we wanted to find the volume of a cone. Notice how the volume of a cone is this lovely thing right here where we have both dH/dt and dR/dt. The problem is we don't know what dR/dt is, so that's where our solution of using substitution in geometry comes into play. I have a radius of 5 feet and my height is 10 feet. All right. And we're trying to figure out how fast the water level is rising when the water is 6 feet deep. So we're trying to figure out what this is right here. And we have some R that we don't know. If I do that, notice how if I were to drop this down, I have similar triangles. I have the whole cone, which is going to be 5 over 10. So 5 is my radius, 10 is my height of my large cone. And then my small triangle right here is R over H. So R over H. Now remember that we don't know what dR/dt is, so I'm going to solve for R so that I could use substitution here. If I solve for R, I'm going to get 1/2 H is equal to R. I simplify down the 5 and the 10, so that's 1/2 H. It's equal to R. All right. So instead of 10, we want when this is 6. And 5, we don't need her anymore. All right, so remember that the volume of a cone is 1/3 pi r squared h. Well, we don't know what R is, but we did use substitution here to figure out that 1/2 H is equal to R. So I'm going to use that to help us. Oops, forget an H. Then I'm going to simplify that. So 1/2 squared is 1/4. 1/4 times 1/3 is 1/12. Pi. We have H squared and H, so that's going to be H to the 3rd. And notice how here 1/12 pi h to the 3rd we have one variable, aka h. And lucky for us, we know what dHdt is because that's what we're trying to find. And we know what dVdt is because that's 2 feet cubed per minute. If I take the derivative of this, that's going to be dVdt is equal to 1/4 pi h squared dHdt. And we want to figure out what dHdt is. All right, so I have dVdt being 2 feet cubed per minute is equal to 1/4 pi. H is now 6, but this is 6 feet square. Let me not do that. Wait, yeah, that's good. 6 feet square. And then dHdt. All right, so I'm going to multiply by 4. That gets rid of that. That's going to give me 8 here. And then I'm going to divide by pi and 36. And don't forget that this is feet square, so this is feet square. And the top is feet cubed per minute. If I simplify that, notice how the feet, 2 of the feet will go away, which means I'm only left with feet per minute, which once again is what I want in terms of my height. So my final answer is 8/36 pi feet per minute. Of course, you can simplify the 8/36 by dividing by 4. So if you do that, so that's going to be 2/9 pi feet per minute, which is going to be dHdt whenever h is 6 feet deep. Yay. All right, number 8. We have a woman that is 6 feet tall and she is walking at a rate of 3 feet per second away from a light that is 45 feet tall. So I have a light. She's 45 feet. We have a girly. She's 6 feet. And she's walking at a rate of 3 feet per second away from the light. So she's moving away from the light. When she is 25 feet away from the light, at what rate is the tip of her shadow moving? And at what rate is the length of her shadow changing? So we have the tip of her shadow. And we have the length of her shadow. So her length and then the tip of the shadow. All right, so I'm going to have this be X right here and let this be Y right here and see what I could do in terms of, let's say, similar triangles because we have similar triangles going on. Then here's my little shadow. I know, it's not the best drawing, but you get the idea. If I were to look at my big triangle, I'm going to have 45 as my height, and I'm going to have X plus Y as my base. If I were to look at my smaller triangle, I'm going to have 6 as my height, and then I'm going to have Y as my base. I'm going to cross multiply. 45Y is equal to 6X plus 6Y. And then I'm going to move the Y over. So I have 39Y is equal to 6X. All right. So that's going to be my equation. That's going to relate my 2 variables. Now I'm going to take the derivative with respect to time. So that's going to give me 39 dy dt is equal to 6 dx dt. Notice how I didn't need the 25 feet away. We did not need her. All right. She was a lot of mumbo jumbo. We did not need her. Instead, we know that she's walking at a rate of 3 feet per second away from the light. So here she is. She's walking away from the light. So looking at this, that's going to be my X value. She's walking away here. So this tells me that dxct is going to be 3. Which means if I want to find out what dy dt is 18 over 39 feet per second. So this right here, dy dt, represents the length of her shadow changing. So this right here. Now, part A says we want to find the rate of the tip of her shadow that's changing. So to find that, we know that that was x plus y. And if I were to take the derivative of that, that's dx dt plus dy dt. We already know that information. Dx dt is 3. And then dy dt is 18 over 39. So this right here represents the tip of her shadow moving. So all of this right here. Now, as a visual, what I want to do is show you Mr. Homer Simpson with this little applet right here. So notice how Homer, he's moving. And you can see here in blue, that's going to be his distance moving from the lamppost. And then we have the shadow tip in gray. Crazy, I know. So that's an example of the lamppost problem. All right, that's it for this video. In the next video, we'll talk about other related rate problems that are a little bit more complicated, but not by much.